Hi, welcome to Verbling Advanced Physics class. For those of you who've been waiting, I'm so sorry for the delay. So go ahead and click on that green Join Class button and join me for some physics today, and I look forward to seeing you soon. Hello, everyone.
Hi. Oh.
It's so good to see all of you.
Hello. Hello.
Hi.
Hi, teacher.
Hello, everyone.
Hello, teacher.
Thank you.
How are you
Hi.
today?
Good, thank you. How are you? Is anyone else hearing a really big echo, or is that just me? I'm hearing a big echo.
I'm here as well.
Okay. So everyone, please make sure to mute your microphones. I'm not sure who's echoing, but hopefully we can get that ended soon. All right. Good. Can everyone hear me okay?
Yes, I can hear you.
Okay, good. Do you guys all do you guys all hear that huge really everything I say repeats, or is that just me that's hearing this?
I heard that, but not anymore.
Okay. I'm going to try logging out and logging in again and see if that works. Give me 1 second, guys. Sorry for the technical problems.
Now the screen is white. No?
Teacher. Libby, are you okay?
Yeah, I'm okay. I'm just experiencing a huge echo where everything I say repeats 10 seconds later.
Mm-hmm.
Do you hear that?
I don't hear. I hear well.
Okay, well, I'll try taking off my headphones then.
I don't hear. I hear well.
Okay, I'm not sure why I'm experiencing this problem, but sorry, give me 1 more second and that'll hopefully be okay. I'm sorry, I'm having some pretty bad technical problems.
Maybe she come? Yes. Teacher, what's the problem? You okay? Libby, what happened?
Okay.
Okay.
Can you guys see me now?
Yes, very well. Yes.
Okay. Sorry, I figured out the problem. Verbling is making some changes to their website, and so if you have the Verbling website open and then you open the Hangout window, it will echo. So I figured that out. So thank you so much for your patience. I really appreciate it. Okay, so now that we're all here, I'm very excited to be working on some physics with you today. And please keep in mind that this is an advanced class. That means the level of vocabulary will be fairly high. So if you feel a little bit lost, that's totally okay. You can just spend some time and review the materials on your own. Feel free to ask me questions whenever you want to, but keep in mind that I may be using a more advanced level of vocabulary and discussion than you are used to in my previous classes. So welcome everyone, I'm Libby. For those of you who don't know me, I am American, but I live in France right now. I studied human biology for my bachelor's degree, so I did a pretty broad curriculum that involved biology, anthropology, sociology, and I also studied a lot of chemistry and physics. So for Verbling, I decided to share with you guys some basic science knowledge, and we can work on some vocabulary together so that if you're interested in science, you can begin studying those science topics in English. So I would like everyone to tell me, please introduce yourselves to me so I know you. So if you could tell me your name, where you are right now, and your favorite thing that you have studied in school, your favorite subject, or maybe your favorite current event or historical event or something that you have studied in school. So I'm Libby, I'm in France, and my favorite subject in school is physics. I really like studying mechanics. So let's see, do we have Ashraf here?
Yes. How are
Ashraf,
you?
good, how are you?
I'm Ashraf. I'm from Jordan. My favorite subject in school, math.
Great,
But
awesome.
I don't like physics and chemistry.
Okay, okay, cool. Let's see, we have Diego here. Diego, are you here?
Hi, yes. Could you hear me?
Yes, I can hear you.
Okay. Yes, I'm Diego from Spain, and my favorite subject is geology. Actually, I'm geologist, and I like science subjects like geology, biology, and something like that.
Great. Well, thank you so much, Diego. It's nice to have you here.
Yeah.
Okay, Gustavo. Hello, how are you?
I'm fine, thank you. I'm from Colombia, and my favorite subject is history and geography.
Great, cool, thank you. Okay, hi, Wen, how are you?
Hi, Libby. I'm fine. I'm from Vietnam, and my favorite subject was chemistry.
Great, cool. Okay, Ilyas. Hi, Ilyas, how are you?
Fine, and you? Thanks.
Great, I'm doing great. So can you tell us your name, where you are, and your favorite subject in school?
Sure. I'm from Turkey, mostly. And I study at Union University at Department of Computer Technology. My subject is computer programming. Yeah, I say.
Cool, great.
Another, no, computer technology, yeah, computer programming.
Cool, interesting. Thank you. Okay, Manuel.
Yes. Hello.
Hi.
My name?
Just so you know, you might want to move your microphone a little bit farther away from your face because when you
Yes.
breathe, it
Yes.
makes some noise. So sorry, go ahead.
Mhm. My name is Manuel Ángel. I live in Spain, more exactly in Canary Island. Canary Island is located in the northwest coast of Africa, near Morocco. Mm, I've studied telecommunication engineer. I get the degree 5 years ago, and I just right now I am working it. My preferred subject or topic in the school was electronic and physical, and math too. Mm, I enjoy very much studying this topic when I was studying in
Cool.
the university. Mm.
Wonderful. Thank you so much. Okay, Simona, I think is next. Hi, Simona. Can you hear us? Okay. I see. Okay, Simona, I can see where you typed in the verbal in classes box, but we can't hear you. So I'll assume that you'll be participating in a written way. But if you find a way to make your microphone work, go ahead and jump in and let us know. Okay, Tom, are you here? Tom? Okay, I think Tom is also maybe working on, Tom, you might be working on your microphone as well. So again, let us know if you figure that out. Okay, and then is it Zeke? I'm sorry, I'm not sure how to pronounce
Hi,
it.
teacher. How are you?
Good, how are you?
Thank you very much. I'm from Istanbul. My favorite subject is article driver. Three.
Cool, thank you.
Thank
All
you.
right, nice.
My job is engineering about in construction.
Great. And sorry, can you say your name for me one more time?
Again?
Zeke?
Yes.
Okay,
No,
good.
no. Zekai. Zekai. If you want to spell, Zekai.
Zeke.
Good. Congratulations.
Okay, thank you. Got it. Okay, and then Simona, great. I can see your comments in the chat, so we'll just go ahead and have you participate that way. Thank you. Okay, so we're going to get started. And I thought that I would start out by telling you guys some of my favorite and also some of the most basic knowledge in physics. So I think, is it Diego? One of you said that you don't like physics.
Mm, physics. Yes, I like one part of the physics, but in any occasion, in any situation, physics was difficult for me. It's because there is a abstract part of the subject, and it's maybe for that.
Yes. Yeah, I understand. Well, I won't be offended if you get bored and leave, but hopefully I will make it interesting enough that you will like it. So, I wanted to just go over Newton's laws of motion. So, Sir Isaac Newton was a British man who, he was famous. There's this famous myth that he was sitting under a tree and an apple fell on his head, and this was his sort of revelation about gravity and the way the world works and the way bodies are attracted to one another. So I found a web page that I think has a really good basic description of Newton's three laws of motion. A lot of classical mechanics, which is what we call the older branch of physics, a lot of classical mechanics that all of us learned in school use these three laws of motion. In modern physics, physicists have moved a little bit away from these laws because we've found that a lot of things are more complex than we expected. But the physics that most people still learn in school is largely based on these 3 laws. So I'm pasting a link to this webpage into where it says Verbaling Classes. So if you could open that link, we're going to read through this text together, talk about some parts we don't understand, and hopefully get a good understanding in English of what Newton was thinking when he came up with these laws of motion and what these laws of motion mean for the rest of physics. So please open that web page that I posted for you, and we'll get started with going over that material. All right, so this is the web page. Is everyone able to open this page?
Yes.
Okay, wonderful. So this is actually a website that's designed for children, but I assure you that the content is completely accurate, and I find it's best to start at a basic level, and then we can add complexity. We can add complexity based on how much we understand. So I think this is a really, really well phrased description. So I'll read the first paragraph for you guys, and then we'll take turns reading the rest of it. So Newton's laws of motion. There was this fellow in England named Sir Isaac Newton. A little bit stuffy, bad hair, but quite an intelligent guy. He worked on developing calculus and physics at the same time. During his work, he came up with the 3 basic ideas that are applied to the physics of most motion, not modern physics. The ideas have been tested and verified so many times over the years that scientists now call them Newton's 3 laws of motion. So does anyone have any questions about this paragraph? Anything you want me to explain or anything you don't understand so far? Makes sense so far? So Isaac Newton was a physicist who came up with these laws of how things move, how things interact with each other. And like I said, these laws apply to the physics of motion that we learn in school. They don't typically apply to modern physics. Modern physics works on things like there's quantum physics, which is for very small things, relativity, which is for very large scales, and then there are things like string theory that I just totally don't understand, that look in more detail at how things work. But these are some basic things that we're going to go over first. Okay, so Newton's first law, very basically, is just, I think it's referred to as the law of inertia. So it just means that if something's sitting still, it's just going to stay there until you push it. If something's moving, it's going to keep moving until you stop it. So that's the basic understanding of Newton's first law. Can someone please read this paragraph out loud for us, Newton's first law?
I can.
Okay, wonderful. Go ahead.
First law. The first law says that an object at rest tends to stay at rest, and an object in motion tends to stay in motion, with the same direction and speed. Motion or lack of motion cannot change without an unbalanced force acting. If nothing is happening to you and nothing does happen, you will never go anywhere. If you were going in a specific direction, unless something happens to you, you will always go in that direction forever. You can see good examples of this idea when you see video footage of astronauts. Have you ever noticed that their tools float? They can just play them in space and they stay in one place. There is no interfering force to cause this situation to change. The same is true when they throw objects for the camera. Those objects move in a straight line. If they threw something when doing a spacewalk, that object would continue moving in the same direction and with the same speed unless interfered with. For example, if a planet's gravity pull on it not. This is a really simple way of deceiving a big idea. You will learn all the real details and math when you start talking more advanced class in physics.
Okay, perfect. So you can see that little picture next to the paragraph. It has a little blue circle, and it says, with no outside forces, this object will never move. So if you just have something and you know, let's say, this is my water bottle. I just put it down, and unless I touch it, it's never going to move. It's just going to sit there. But with no outside, I think what's more confusing is that with no outside forces, a moving object will never stop. So that's the second part of that picture. It has a little blue circle again, and it says, with no outside forces, this object will never stop. I really like the example of astronauts because in space, it's a vacuum, which means there's no force, there's no outside forces at all. And when astronauts throw something in space, it just goes like this. It just goes in a straight line, and it will keep going that way forever. Why do we not see that on our planet? On Earth, why do things stop moving? So for instance, if I have my water bottle and it's sitting on the table and I push it, it only moves a little bit and then it stops moving. Why does it stop moving?
For the gravity?
Yes, that's part of it. So on our Earth, we experience gravity. Without gravity, we would be like astronauts. We would be floating around. But we experience a force that's called gravity that pulls us towards the Earth. So I'm sitting in this chair because gravity is pulling me down. The reason I'm not moving is because the chair is also pushing up on me. So gravity is pulling down on me, but my chair is pushing up on me, so I'm sitting still. I'm sitting in one place. Does anyone know the name of the horizontal force that makes my water bottle stop when I do this?
F.
Good, friction. That's great. So friction, this table provides friction. That means that it's not a smooth surface. On a molecular level, this table is very rough compared to something like ice that has less friction. So because this table has friction, when I push my water bottle, it stops moving. So it only goes a little bit and then it stops. If there were no friction on this table, what would happen if I pushed my water bottle and let it go? What would happen if there were no friction?
It'll move forever.
Yes. So it would move forever. So a good situation that approximates no friction is an ice-covered lake. If I'm sitting on an ice-covered lake and I push my water bottle onto the lake, it will keep going for a very long time. And it will eventually stop because ice does have some friction, but ice has way less friction than something like this table. So the reason that things stop on our planet is usually because they are being acted on by gravity or because they are being acted on by friction. So gravity and friction are very important ideas that tell us why Newton's laws can sometimes be confusing on Earth. Astronauts have no gravity, and astronauts have no friction in space, in the air, in space. So that's why Newton's laws of physics apply in a very pure way to astronauts. So things that are moving keep moving, things that are still stay still. So does anyone have any questions about Newton's first law? Any questions about vocabulary, any words in English that you find confusing when it comes to this? Okay, great. Is anyone totally confused? Is anyone totally lost? No. Okay, good.
Clever boy.
All right. So we're going to now go over Newton's second law. So who would like to read his second law for us?
Second law. The second law says the acceleration of an object produced by a net applied force is directly related to the magnitude of the force, the same direction as the force, and inversely related to the mass of the object. Inverse is a value that is 1 over another number. The inverse of 2 is 1 third.
It's either 1/2 or 1/2.
1/2. The second law shows that if you expert the same force on two objects of different mass, you will get acceleration, change in motion. The effect, acceleration, on the smaller mass will be greater, more noticeable. The effect of a 10 Newton force on a baseball will be much greater than the same force acting on a track. The difference in effect, acceleration, is entirely due to the difference in their masses.
Perfect. So I love this law because it gives me a formula that I can apply to a lot of situations. So the second law, we always say in my class, just F equals ma. Force equals mass times acceleration. So if you exert the same force on two objects, one of them is big, has big mass, and one of them has small mass, the one with the smaller mass will have a greater change in acceleration. So this might be a good time to go over some basic measurements we use in physics. So the first thing is force. Force is measured in a unit called newtons. You can probably guess who that's named after. It's the same guy who came up with this law. And we have, I'll actually answer this question that we have in the chat because it's very interesting. So Thomas, the second law does apply to rotation, but there's a special, there's a different way we measure the inertia. So if there's something that's rotating like this, the mass and the shape of the object change how it accelerates. So it's definitely something you can Google to look up. I don't remember the exact formula right now, but instead of mass, we have a coefficient of inertia that's based on the mass and the shape of the object. Okay, so anyway, so we have force. It's measured in newtons. Force is kind of hard to describe, but for now we can think of force as just how hard you push on something. So I can push on something lightly with a little bit of force, or I can push on something hard with a lot of force. Okay, so force is just how hard we're pushing on something. And let's see, and then there are different ways we can measure the behavior of objects when we apply forces to them. The ways we can measure objects' behavior are position, velocity, and acceleration. Does anyone know what position means? What does position mean?
Location.
Perfect,
Usually,
yes. Yeah, position, one is right. Position is just something's location, just where it is in space. So right now, my position is in this chair. If I stand up and go somewhere else, now my position is different. It just refers to where something is in space. Okay, velocity. Does anyone know what velocity is?
Speed.
Fraction. Fraction.
Good. So velocity is speed. Speed. And all of these measurements have a direction. So position has a direction because I can be standing 2 meters to the left of where I am now, or I could be standing 2 meters to the right. So position has a direction. Velocity also has a direction. So if I'm driving on the highway at 100 kilometers per hour, I have my speed is 100 kilometers per hour, but my velocity also refers to which way I'm going. So I could be driving east, or I could be driving west. So my velocity is 100 kilometers per hour to the east, because that's the direction that I'm driving in. So they both, position and velocity, they both have what we call direction.
this is a vector.
Yes, it's a vector. So these are what's called vector measurements.
Directly rotational.
And they have direction.
Mm-hmm.
Vector measurements have direction. So the third vector measurement of an object's behavior is called acceleration. Does anyone know what acceleration is?
Acceleration.
The change in velocity.
Velocity.
Good.
Velocity.
Perfect. So the acceleration, good, is the rate of change in velocity. So if something is speeding up, it has a positive acceleration. If something is slowing down, it has a negative acceleration. So positive and negative are also two words that I'll be using as we get into more physics stuff. But acceleration is how fast the speed or the velocity of something is changing. So the classic example of acceleration is when you have a car, sitting still on a road, and then you slam on the accelerator, you slam on the gas, and the car goes and speeds up. So that's what we think of when we think of acceleration, and that's a very good example.
Acceleration, it is an increasing of velocity.
Yes, acceleration can be an increasing of velocity, or if it's negative, it can be a decrease in velocity.
Yes.
We sometimes use the word deceleration to refer to a decrease in velocity, but we'll see later that leads to a lot of inconsistencies. So I prefer to use, and physicists prefer to use, the word acceleration to describe both positive and negative acceleration. So acceleration can describe both speeding up and slowing down. Typically, speeding up is the normal example of acceleration, but it can also refer to something slowing down. Okay, so let's get back to Newton's second law after that little explanation. So the second law is force equals mass times acceleration. And question in the chat from Ria, if the car moves at the same speed, then the acceleration is 0. That's exactly right. So I can be driving at 100 kilometers per hour, but as long as my speed is staying constant, my acceleration is 0. So as long as the velocity is constant, whether that velocity is 0 or whether it's 1 billion kilometers per hour, as long as it's constant, as long as it's staying the same, the acceleration is 0. So yes, that's correct. Okay, so Newton's second law, force equals mass times acceleration. That means that if I, let's say I want to play soccer. I guess people call it football in most of the world, but in America we are stubborn and we call it soccer. So if I kick a soccer ball, it will go pretty far. If I kick it really hard, the soccer ball will travel, it will go somewhere. Let's say though that my car breaks down, and I'm really angry, and I hate my stupid car because it's not working, and I kick my car. If I kick my car, is it going to move?
Are you nervous?
No.
So no, my car will not move if I kick it. But a soccer ball will move if I kick it. And why is that? Why is that the case?
Because
Because of the mass.
Good. So they have very big differences in mass. A soccer ball has small mass, so when I apply a force to it, it will have a greater acceleration. It will speed up faster than my car, which basically will not speed up at all, because my car has a much, much greater mass than my soccer ball. So this law is huge. When Newton came up with this law, it was absolutely incredible because this formula, a formula is when we express something mathematically. So when we have an equal sign, that's called an equation. Equation is, I'll go back. Equation is something with an equal sign. And then a formula is an equation with symbols. So F equals ma, we refer to this as a formula. Okay, so this formula it applies to a large variety of situations, and people were pretty amazed to see this when Newton came up with it. So does anyone have any questions about Newton's second law? Any questions? So does it make sense to you guys? Do you find this useful to know, or not really?
I think everybody knows this formula because it is studied in the school when you are a kid.
Yeah, but it's hard to explain it in English.
I don't hear, Libby.
Can you hear me now?
Now, yes.
Yes, I can hear you.
Okay, cool. So I'm sure the formulas in general will be more easy for you guys because you have studied them in school. So I guess what's more difficult is the English vocabulary that surrounds some of these concepts.
Yeah.
So make sure to ask me if you have any questions about vocabulary. All right, so we'll move on to Newton's third law. Who would like to read on this webpage the paragraph about Newton's third law?
Unnecessary.
Would anyone like to read this for us?
Okay, me. Diego.
Okay, great. Go ahead.
Third law. The third law says that for every action force, there is an equal and opposite reaction force. Forces are found in pairs. Think about the time you sit in a chair. Your body exerts a force downward, and that chair needs to exert an equal force upward, or the chair will collapse. It's an issue of symmetry. Acting force encounter other force in the opposite directions. There is also the example of shooting a cannonball. When the cannonball is fired through the air by the explosion, the cannon is pushed backward. The force pushing the ball out was equal to the force pushing the cannon back. But the effect on the cannon is less noticeable because it has a much larger mass. That example is similar to the kick when a gun fires a bullet forward.
Great, thank you. So Huynh asked earlier about, or someone mentioned recoil earlier, and this is when that sort of comes in. So when a gun fires a bullet forward, then there's a backward force, there's a recoil on the gun, and on as a result on you. So action reaction force. We have a question in the chat about what exerts means. Exert is the same thing as apply. So if you apply a force, or so basically if I push something, I'm exerting a force, or I'm applying a force. So when I say when we talk about forces being exerted on things, that just means there's a force acting on it. There's a force and it's doing something to it. All right, so another question in the chat. Without friction, will it be possible for you to kick your car and would it move? Great question, really good question. Without friction, if I kicked my car, it would move. And that's a very good point, but it would move at an extremely slow velocity. So it would move maybe something like this. Like about that fast, maybe. So yes, it would move a little bit. The real reason my car does not move is because there's friction, and also because usually a car has a parking brake on when it's stopped. So great question, and that's actually what brakes do. The reason that brakes work, the reason that brakes stop things, is because they apply friction. So that's a big innovation. Basically, the brakes are a big innovation in the idea that they use Newton's laws to stop things. Okay, so Newton's third law I think is pretty straightforward. I think the reason that students get confused about Newton's third law is because sometimes it's confusing to determine which thing these forces are acting on. So sometimes people get confused and they try to make diagrams and they don't understand which force each force is acting on. My advice when you look at Newton's laws, and I'm sure you've done this in school as well, is to always be drawing diagrams. So draw a diagram of the person and a diagram of the car, and diagram which forces are working on each of those things. It will help resolve some confusion when it comes to this law. My favorite thing that people always say about this law is if someone punches you, if someone punches me in the face, I'm exerting just as much force on them as they're exerting on me. So technically, I'm punching them back just by letting them hit my face, because I'm also exerting the same force on them. So my friends always used to joke about that one. That's one way to think of it, I guess, but I think I'd still rather not get punched in the face. All right. Cool. So we are going to move on. I'm trying to open the next web page. Okay. So we're going to just do a quick quiz, go over some questions about this. So you can either click and go to the quiz on the bottom of the page, or you can click on the link that I just posted for you. And we'll just do this quiz quickly together. It's pretty easy. I think you'll find it pretty simple. And hi, Elias. Welcome back.
Hi.
Okay. So this quiz says, the first question says, an object at rest will blank if no outside forces are applied. What's the answer to this one?
Stay at rest.
Stay.
Yes. An object at rest will stay at rest if no outside forces are applied. Correct. Yay. Okay, next question. Momentum is related to Newton's first law. We haven't talked about momentum yet, so this is a little tricky. Any ideas?
What is the
So this is true. Um, momentum is related to all of Newton's laws. Newton developed his laws of motion by considering momentum. And just as a note, the word momentum refers to the product of something's mass and its velocity. Momentum equals mass times velocity. And so a big truck that's moving at 10 miles per hour has a lot more momentum than a bicycle that's moving at 10 miles per hour because the truck has a lot more mass. So momentum is a way to take into account the mass and the velocity of something. So how big it is and how fast it's going. So Newton looked at momentum when he looked at all of his laws, and it's a very important concept, pretty central to what he did. All right, so I made the text a little bigger. Okay, next question. More force is required to accelerate an object with greater mass than, sorry, I'm going to need to make this window bigger, than a smaller mass. So more force is required to accelerate an object with a greater mass than with a smaller mass.
True.
That's true.
Yeah, that's right. This is true. As the question says, it is more difficult to accelerate an elephant than a paperclip because it has more mass. All right, next question. Newton's second law uses the formula, which one?
The third one.
Third, yeah, C.
Yes, it's this one. F equals ma, force equals mass times acceleration. How about E equals mc squared? Whose formula is that?
Einstein.
Yes, that's Einstein when he was developing his theory of relativity. That refers to the relationship between energy, E, and mass, M. He found that energy and mass are related by multiplying by a constant. Does anyone know what this constant C is?
Einstein.
It actually refers to a real measurement in real life. So C here is actually the speed of light. He found that energy and mass are related by the square of the speed of light. So how fast light travels is expressed by C. I think it's 3 times 10 to the 8th meters per second or something. So that's Einstein's formula. But yes, this one, Newton's formula was F equals ma. All right. Next question. Is acceleration the same thing as velocity?
False.
Nope.
Yeah, no, not at all. What is the relationship between acceleration and velocity?
The difference of velocity is divided by the time.
Good. So acceleration is the rate of change in velocity, or acceleration is change in velocity per unit time. So as it says here, acceleration is the measure of a change in velocity over a period of time. And as we said, acceleration can have a positive or a negative value. Cool. Next question. Is mass a vector measurement?
No, false.
Nope.
Yeah, that's correct. Mass is not a vector measurement. Vector measurements need both an amount and a direction. So mass only has an amount. So you weigh a certain amount of kilograms. You can't weigh negative 100 kilograms. That doesn't make any sense. So because it has no direction, mass is called a scalar value. What are some other things that take scalar values? What's an example of a scalar? Something that's not a vector.
Es que el valor, for example, the weight. The altitude.
Weight is actually a vector measurement because weight actually refers to how much force is acting on something. We can talk about that later, but pounds are actually a measure of weight, which is really strange. But kilograms are a measure of mass, and that is a scalar measurement. Another example of a scalar measurement is speed. So speed has no direction. So some vectors would be position, velocity,
height,
acceleration. Height's another way of saying position, so that's good. Weight is a vector. And then so scalars include mass, speed,
time.
I guess time is a little bit complicated because you can technically have negative time. I would not put time in either category, actually. Time is a little bit complicated. But those are some examples of vectors and of scalars. So vectors and scalars are opposites. Vectors and scalars are opposites. Yes, and Ria, good. Momentum is a vector. Perfect. Yes. Momentum has both a magnitude and a direction. We had a question in the chat earlier, what about the formula A equals PR squared? I'm not sure what that refers to. There are a lot of measurements that are related to the radius of something squared. I'll look it up afterwards and see what exactly that was trying to refer to, because it's not a formula that I'm immediately familiar with. All right, cool. Vectors and scalars, great. Next question, is gravity a vector measurement?
True.
Yeah, so gravity is a vector measurement because it acts in a certain direction. In reality, gravity actually acts towards the center of the Earth, right? We're all being pulled by gravity towards the center of the Earth. So because it has a direction, it is a vector. All right, the SI units for force. So when we say SI units, that means the units that physicists as a standard use to measure something. So what are the standard units that we use to measure force?
Newtons.
Yes, that's exactly right, actually. So we measure force in newtons. And we'll talk more in a future class about what exactly a newton is. But yes, newtons are the unit that we use to measure force, the same way that we measure mass in kilograms, and we measure velocity in meters per second. All right, last question. Does gravity always change the velocity of objects?
No, false.
That's totally right. Oh, well,
True.
I would not agree with this question. Yeah, I don't agree with that answer. I think that gravity, so what the question meant to ask was, does gravity always change the velocity of objects in the absence of other forces? Well, yeah, of course. You know, if there's only gravity and there's nothing else, it will change velocity. But I'm sitting in my chair, gravity is acting on me, but so is my chair. My chair is pushing up. So if there are other forces present, gravity does not change the velocity of objects. All right, so that's all the time that we have for physics today. You guys were very good at this, and I'm going to come up with a little bit more advanced topics for next physics class. Definitely, I always love your feedback about what you'd like to study, so let me know. There's a lot of stuff in physics that we can talk about, and I'm happy to go over it with advanced students. So just keep me updated on what you want to be working on, and thank you so much for being here today.
Thank you.
Thank you.
All right. See you guys.
See you.
Bye.
Bye bye.
Bye.